So let's begin by calculating all of the DE with respect to DWIJ. First of all, let's recall that our output y, this is what it looks like, right? We've computed our output. It's the result of our convolution. Now this is kind of the meat of it all, and the most important part here. Since each weight of the kernel affects our output and contributes to the loss, we need to compute the total derivative. So we need to compute the derivative with respect to every output, with respect to every weight that we're considering. So here we're computing the derivative with respect to output y11, with respect to output y12, y21, and y22. And this is what each and every single one of these terms represent. And then what we can do is we can apply the chain rule. So here we say that the derivative with respect to our error, the derivative of our error with respect to dWij can be decomposed as the chain rule for every single one of our elements. So we can expand this for all ij's, right? We have 4 possible ij's. We had our w11, w12, w21, and w22. So we can extend this and replace all of the ij's with the indices that we're interested in. Now we're going to focus on just one set, and the rest of them you can go ahead and do them later on your own time. So let's focus on the set where we have the ij indices set to 1, 1. And again, as a little recall, I'm going to put the output of our network that we originally computed here. So what are we interested in computing? We have to compute dE with respect to dy11 and the derivative of y11 with respect to w11. So let's start with this term here. Right? If we want to compute this term, again, recalling that this is our output, so we want to take the derivative of y11, which is this term in blue, with respect to dw11. So we treat every variable as a constant except for w11. And if we look at this term here, we see that we have w11 over here, and all the other ones are not w11. So again, recall to calculus, all of these terms go to 0, and the only term that we get is the derivative of x11 w11 with respect to w11, which turns out is just x11. And we can do this for every single one of these terms. So for our dy12 with respect to dw11, again, if you look at this term here, you would find that you get x12. Here, we look at the contributions for w11, we get x21 over here. And here we get our x22 over here. So we can expand this for every one of our terms. Now what's interesting is that we need to compute the error with respect to y11. And because of the loss that we defined, we know that this error is simply the difference between what our network outputted and what we were predicting. So we can compute this numerically. So this is the following result that we get. So what we see is that the derivative of our error with respect to our inputs can really just be found by using a combination of our inputs and the outputs, because, again, the derivative is simply the output minus the ground truth that we had. And this just so happens to be equivalent to performing the following convolution. We take our input and we convolve them with the derivative of the error with respect to each output. And again, this can be expressed as a matrix multiplication like we saw before using our strategy. So it turns out that the backward pass, or the gradient, is actually relatively cheap to compute as well. Now this is another point that's important. We calculated the derivative of w11, and we can update our parameters. But it's also important to calculate the derivative with respect to our inputs. And why would we want to compute the derivative with respect to our inputs? So if the input is the actual input to our network, this cannot be tuned. But like we mentioned earlier, we can have our neural network be composed of multiple layers. So in fact, the input to one layer could have been the output from a previous layer. And therefore, if we constructed our graph would be much larger than this. And this input here would actually be connected to other weights that we would have to tune. So we would have to take into account the derivative of here as well. So building our graph, we follow our derivative. We computed the derivative with respect to our weights. And now we're going to compute the derivative with respect to our inputs xij. So we need to compute the derivative of the error with respect to xij. And again, we have this concept of total derivative. So now it's the exact same formula as we had before, but instead of having the wij's, now we have all of the xij's. And we have we have more xij's than we had wij's. So again, we're going to focus here on the case of 1, 1. So just the derivative of the error with respect to our first input. So we replace all the xij's with 1, 1. And you would have to compute this for every pair of ij's that we have for our input. So expanding, here we have our total derivative that we're trying to compute. And now we want to compute this part here, dy11 with respect to dx11. And again, recall that our output, y, is given in as this expression, where this point here is our y11. So now we want to perform the same derivative that we were calculating before, but this time with respect to x11. So if we look at this equation here, we see that x11 is here, and it turns out that dy11 with respect to x11 is w11. Now, differently to what we had before, all of these other terms, if you look closely, there is no more x11 involved in the rest of our outputs. So these terms all stay at 0, and our derivative is only this w11 here. And again, this is really by looking at dy12, you see that there's no contribution to x11. So we don't compute these different errors, and so our error with respect to our first input is simply w11. If you expand this, and you continue doing this, this is the result that you would get. So this was our first the example that we just did, the derivative of the error with respect to x11. It was our w11 times the derivative of the error that we computed. And now you can see all the other terms that we compute. And you might notice that there is some kind of symmetry going on here, right? And this is due to the structure of the convolution. And again, the different inputs will contribute differently, and this is because of what we've seen with the padding. So this is why, for example, if you had a full convolution, it might be useful because now you can have all your parameters contributing equally. But we see here that our parameters don't necessarily contribute equally, and we have some kind of symmetry. And it turns out that this is equivalent to calculating this following operation. So remember how we shaped our weights vector such that we were able to do the matrix multiplication? It turns out that if you take the transpose of that and you do the matrix multiplication with the error, so again, this is just the difference between the ground truth and the output of your network, you get exactly this result. And this relates to the transpose convolution that we were talking about earlier today. This is really the operation of the transpose convolution. So it's a little bit different to the convolution that we're used to, but it directly relates to the convolution in that you take that convolution operation as a matrix, you calculate its transpose, and then it turns out that it's another matrix multiplication. Right, so this is the transpose convolution we were talking about. So now let's put it all together. So our forward pass can be computed via our matrix multiplication. So again, we unrolled our input. We constructed our matrix W with respect to our weights. We can then calculate the gradients with respect to our kernel via our convolution, which can also be expressed as a matrix multiplication. And finally, we can compute the gradients with respect to the inputs by this transposed convolution. And these are the three kind of key things that you need to do gradient descent in convolutional neural networks. All right, so we're kind of done with the math for now. And this is where it's important for me to remind you of a few things. First of all, most modern frameworks implement this for you. When you're coding in PyTorch, when you're coding in TensorFlow, you almost never have to implement this yourself. In fact, if you find yourselves implementing this for other reasons than just learning, you're probably not using the frameworks properly. So it's still important to understand it at least once, right? And you're here today to be learning more about convolutional neural networks, and to go through this math really gives you some kind of intuition as to what's going on under the hood. And again, if some of these details were a bit loose, take the time to go back and read them on your own time. And keep in mind, this was for a single layer. We had no bias. We had no padding. It was kind of the simplest example we could have derived. And it really isn't that simple. So it might give you an appreciation as to what's really going on when you're doing convolutional neural deep learning with convolutional neural networks. And here I have many different links of papers, blog posts, etc. Some of them inspired me to come up with these slides. I really encourage you to go read up more on it and to really make your own intuition and understanding into what's going on when we do gradient descent in CNNs.
you.